The aim of this experiment is to evaluate or actually it is maybe typo error, typo here, to evaluate, not evaluation, to evaluate the stress concentration factor in a rectangular plate with central circular hole. So maybe here we consider the discontinuity as a circular hole. You may have other kind of discontinuity also. It may be elliptical hole or some other type of hole, or it may be a notch, or it may be a crack or something like that. Whatever you want, you can take it. But in this problem, we consider only the hole as a geometric discontinuity. Now, because of this geometric discontinuity, to estimate what is the stress concentration. So from your course, that is design of machine members, there you might have studied about the stress concentration factor. So if you look at that, the stress concentration factor is function of the width of the plate and the diameter of the this hole. Our geometric discontinuity have the diameter of that hole, and not only that, so it depends upon the dimensions of this plate also. So generally will consider the load line, whatever load here we are applying, that is far away from this discontinuity. So with those assumptions, you can easily find out what is the stress concentration factor in a plate with a circular hole. So if you go to the Google, so if just you type stress concentration, okay, so it's not stress analysis. Okay. So okay, you can see that stress concentration in a plate with a circular hole. So if I go for this, see now I can get a standard tables for all these stress concentration factors. See now something like this here. So if I can select any one of these tables here. Let us say if I take this, okay, you can see that your KT, the theoretical stress concentration factor, is nothing but sigma max by sigma nominal. Here, this is a parabolic kind of curve, so which is varying with respect to d by w. So d by w means where d is the, maybe if you choose some other chart instead of this, it will give what are those parameters also. What is d? What is w also? So again, I'll go back one step. Okay, I'll select the some other diagram which is somewhat clear. Go down. Okay. Yes. Okay, not that one. Okay, maybe what I have given in the document, that is the better one when compared to this. I'm looking for that one only. Yes. Okay, you can see that here. Okay, if I open this figure, what happens to this? I don't know why it is not opening. Anyway, so or else we can pick the some other one here. Okay, right. So you can see here, I have a rectangular plate with circular hole which is subjected to some tensile force here. So in this, the KT value is calculated by sigma max by sigma nominal, what we have seen. So this is the W, that is width of the plate is W, and D is the diameter of the hole. So that means the stress concentration factor will depend upon d by W value. So, but if d by W changes, obviously the KT will also will change. So now in our problem we have taken the d by W is equal to 0.1. We have taken d by W is equal to 0.1. So for that case here you can take the stress concentration factor is close to 2.7. From this curve, for a d by W of 0.1, the stress concentration factor is 2.7. So you can take this one as a reference and we can validate our simulation results, whatever we got, whether that is close to this 2.7 or not. So we can validate that also. So for that, you need to compute what are the values of the sigma naught. So sigma naught is going to be many times. So what you are doing up to 9:30, useless fellows. So here, okay, so to compute that, so from the software we'll get a sigma max value. but we need to compute the sigma nominal stress value, sigma naught nominal stress, which is given by the applied load divided by the area, where the area is given by W minus D into T, where W is the width of the plate and D is the diameter of the hole and T is the thickness of the plate. So now by taking all these parameters, I can calculate the nominal stress. Then from the software, I'll get the maximum stress value. So then that maximum stress divided by this nominal stress should be equal to your KT. So that you have to get around this 2.7, around 2.7. So or if it is deviating from that value 2.7, we try to compute what is the percentage of error. Okay, so this is about this analytical solution, how we can compute the stress concentration factor. So now if I go for this one, so what I can say, okay, so if I come to our experiment here, so he has given a rectangular plate with dimensions 1000 by 500 by 10 mm. So in this B value, actually B is 100, B is 1000, width is 100, and the height is this one A is equal to 500. Maybe here it is written wrongly, so you can make that correction here. A is 500 only, B is 1000. So that's what the meaning of this one. 1000 mm by 500 mm by 10 mm means its length is length, or what I can say, length is 1000 mm, width is 500 mm, and thickness is 10 mm. So this is the dimensions of the plate. That means your A is 500 and B is 1000. Of course, thickness I have not shown this in this direction. In this diagram, thickness I will take it as 10 mm. So the diameter of the hole he has given it as 50 mm. Diameter of the hole he has given is 50 mm. That means in this formula, whatever I take it here, so W minus D into T, W is going to be width, which I will take it as 500. And D, diameter of the hole, we are taking it as 50 mm, and thickness is 10 mm. So applied load, so he has given that in the problem itself. So the load is 1 meganewton. It is subjected to a 1 meganewton of tensile force. So because of that, so what you can do is you can calculate the nominal stress now. Nominal stress value is going to be your applied load, that 1 meganewton divided by the area what we discussed now. So area is nothing but, so 500 minus 50, it is 450, thickness is 10, 450 into 10, we'll get that value. I think I might have calculated that one also. I have shown that in this in this itself, that nominal stress is nothing but 1E6 divided by 450 into 10, which comes out as 222.22 MPa. So once I got this one, then I'll solve the problem in the software. I'll try to compute the maximum stress. So from the simulation, it will be around 306. It is around 306 MPa. So then from that, you can calculate your stress concentration factor is nothing but, not it is 306. It is 612. You are going to get 612. Maybe here is also there is a correction. 612.5. So then if I compute the stress concentration factor, I'll get it as 2.75 mm. Okay, so now we'll see how we can model this one in our FEM software, that is ANSYS. So here, so far whatever we discussed, they are comes under one-dimensional problems. Now we enter into a two-dimensional problems. So here, because you have a rectangular plate, it is an area. So far, you solve the problems on beam and bar elements, so which are line elements. That means they are one-dimensional elements. Now we move on to the two-dimensional problem here. So again, in two-dimensional, you have different types of problems, plane stress, plane strain. Then you have axisymmetric kind of problems will be there. So if I look at this particular problem, this comes under the plane stress problem. Why it comes under plane stress? Because one dimension is very small when compared to the other two dimensions. You can take that thickness is very small when compared to the width and height or length and width of the plate. So therefore, this 10 mm is very small when compared to 1000 and 500. And also the other condition, in order to satisfy the problem as a plane stress problem, always your load should act perpendicular to the small dimension. So here the load is acting perpendicular to the thickness. So this problem satisfies the conditions for the plane stress. So that means I can model this problem using the plane stress approach. So now in that, so to model this plane stress approach, I need to select the 2D elements. So for our analysis in the software, we'll select plane 183 element to mesh or to convert the whatever geometry you have into FE model. We'll use plane 183 elements. Here this plane element 183 elements are a quadratic displacement behavior element which is having 8 nodes. Generally, it will have 8 nodes. Maybe in a special application, you can reduce that 8 nodes to 6 nodes also. But whatever we use in our particular this problem, we'll use only 8 node element. So each node in all those 8 nodes, so each node has 2 degrees of freedom. Those are 2 translations, translation along the horizontal direction and translation along vertical direction. So that is about this element description. So that means here I am selecting a plane element which is having 8 nodes, and then each node is having 2 degrees of freedom. Those two are 2 translations along horizontal and vertical directions. And if you observe this, in previous case we mentioned that there are how many number of elements and how many number of nodes are there in our FE model also. But for this particular one, I didn't mention the number of elements and number of nodes also, because so depending upon the accuracy of the solution what I got, I may change the mesh size. So that means I may change number of elements and number of nodes also. So therefore they are not fixed. That's why I not mentioned. Only I have to use this specific number of elements and this specific number of nodes only for this problem. So that's why I not run that. I not mentioned that in this FE model about that. So here, this is the FE model what I given you. So this is only a sample how I can mesh it here. If you look at this FE model here, see here you can see that here you can see a black kind of thing here. Why we are looking at black color here? Because the size of element is very small when compared to the size of element which is far away from the circle. Why I have to use different kinds of mesh density? So far away from the hole here, this is the size of the element. Here you can see you cannot see the element also here at this location, because so to capture the stress concentration, what we need to do is we need to go for very fine mesh. With the coarse mesh, you are not able to capture the stress concentration properly. So therefore, we need to go for very fine, means the edge length of the element is very small, so that our accuracy of the solution will also increase. But that is not required at the far away locations from this whole surface or from the circumference of this hole. Only in the vicinity of this hole, there is a stress concentration. So I need to refine the elements only in the vicinity of this circular hole. Okay, right. So that is about this FE model or FE mesh, how we are going to get. So now if I move to the software, how I can model this one is, here we first will use that approach. What is that approach we'll use? We'll use bottom up approach. That means first I'll create the geometry, then I'll convert the geometry to the FE model, because I don't know how many number of elements and how many number of nodes I need to create for this plate. So I'll use bottom up approach. That means or the indirect approach, I can say. So first I'll create the geometry, then I'll convert the geometry into FE model. So to create that, what I have to do is I have to create a rectangle first of given dimensions, that is 1000 by 500. Then I need to create some hole here. So to do that in the software, what I'll do is I'll create another solid circular area. Then I'll subtract the solid circular area from this plate so that I'll get a circular hole at this location. Once I got that, then what I need to do is I need to mesh it, and then I need to apply the loads and boundary conditions. So coming to the loads and boundary conditions here, so this is subjected to a tensile load of 1 meganewton. So that means left hand and right hand is subjected to a tensile force of 1 meganewton and 1 meganewton on either side. So, but if I apply something like that, the software won't solve the equations, because if you apply only load, so I think you might have learned. So now by this time you might have learned your FEM course. What are your equilibrium equations are? K into U is equal to F, or K into X is equal to F. Those are the equilibrium equations you need to solve. So in order to solve this, generally if you write the K matrix, it is going to be without constraints, it is going to be a singular matrix. That means the determinant of K is going to be 0. So you cannot solve that k into u is equal to f equation straight away without applying any constraint. So that means here, so constraint means I need to put some constraint on some degrees of freedom. That means either in x direction or in y direction. So, but in this problem, he has not mentioned that. So there is no constraint, something like that. But what I can do here is, so the left support, I am applying a load here. So instead of applying the load here, what I'll do is, I'll constrain the left side of the plate. So if I do that, so then what happens here? If I fix this end, if I apply a force, obviously if I compute the reaction is same as the applied force. So therefore you can represent this model as same as this one. Just this force is replaced by support at this end. So like this, I can solve the problem. So that means, so what I do is, while applying the loads and boundary conditions, what I need to do is, I need to apply a force this end, this side, and I need to constrain this end. So that's it. So first I'll create the area of rectangle, then I'll create another solid circular area, then I'll subtract the circular area from this rectangle so that I can get a plate with hole. Then I'll mesh this area so that I can convert that geometry into FE model. Once I have done that, then I'll fix this end and I apply the force at this end. And also one more thing here is, in the software there is no provision for applying the force here. So then what I do is, whatever load he has given, that 1 meganewton load, I try to convert that one into pressure. So that means, even though he has given it a point load, how it has shown in the diagram here, you can see that here it is a traction force. In this diagram, he has shown this one as a traction force. So that is, it is not applied only at one particular point. So here he mentioned it is a 1 meganewton load, but that is a traction force. So traction force means it is acting over an area. So therefore, if I take this load, area of this end, I'll get that is the force, that is the pressure which it is subjected to. So that is nothing but 1 meganewton divided by this area of this edge. It is nothing but this width is 500 and thickness is 10. So 1 meganewton divided by 500 into 10, that is 5000. I'll get the stress as 200 Newton per mm square. So 200 MPa I'll apply. The pressure is 200 MPa. And also one more thing here we need to remember is, the pressure is acting, here it is a tensile load. If I take a pressure, always the pressure will act towards the body. So it is going to be a compressive load. So in order to convert that one into a tensile load, what I need to do is, I need to give negative sign for this load so that I'll get the tensile load. I can apply it from this location also. So that's it. So like that, I can apply the load. Instead of point load, I can convert this one into a traction load and I'll apply the traction load as a pressure to this edge. And the magnitude of the traction load is going to be this load divided by the area of this edge. So load is 1 meganewton, that is 1 into 10 power 6 newtons divided by area of this edge is 500 into 10. So which comes out as your 200 MPa. Okay. So this is how you can do that. So once you have done that, so from the software you need to pick what is the, like I already mentioned, you need to pick what is the maximum stress value. It should be around 612.5. So then use this calculation to compute the 2 stress concentration factor, and you need to write that one here. So from the graph what I have given here, so from this graph you can pick that stress concentration value. You can write that one here and try to calculate what is the percentage of error. So like this we can do it. So but here in this problem again, so I can model this problem in the software in two ways. One is without using the symmetry. That means I can model here whatever FE model I shown it here. So that is I have not used any symmetry boundary condition. That means I have not make use of any symmetry boundary condition in this plate. So that means, so I model the entire plate. But if I look at this problem here, you can see that the problem is symmetric about both the axes, along the x-axis and along this vertical axis as well as horizontal axis. That means whenever there is a plane of symmetry is there, so I can reduce the size of the problem just by making use of that symmetry. So that means here I can model this one as only 1/4 of the plate and I can solve the problem also. In that way also I'm going to get the same results and same thing. And what you are going to get is, if you use the symmetry condition here, So because of the symmetry, your size of the problem is reduced to 1/4 here. Earlier I need to model the full plate. Now I am modeling only 1/4 of the plate. So that means the size is very less. So therefore the size is less means only I have to consider 1/4 of the plate means your FE model, size of FE model is also very less. That means the number of nodes and elements are also less when compared to the full model. So therefore your computational time is going to be very small when compared to the full model for a symmetric model. So that is the advantage. If I want, I can make use of that advantage also. So in that case, I need to invoke the symmetry conditions in this. So it means I need to model only 1/4 of this plate and then I need to solve for that. So okay, so if time is there, but what I prefer is first I'll show you how to do it in a full model. If time is there, so that is if I am able to complete that one before 9:45, then I'll show you how we can solve this one using symmetry boundary condition also. Then we'll see that. So or else we'll stick to only this one. As far as our recording purpose, we'll take only this one. So that means we'll consider only full model and we'll try to solve this problem. So in the software. So now I'll take you to the software, how I can solve this problem in the software. Okay, so here, so first, okay, okay, before that, what I'll do is, I'll set the title for this one as, say, okay, I want to rename this, so change job name, I'll take it as stress concentration factor or experiment 5, something like that, I'll give the title, experiment 6, this one, I'll give experiment 6, so it comes out as like this, then I'll save this with this name. Then first I'll select whatever element type what we discussed. We can select that. So go to element type, then add, edit, delete. So then you need to add. So here, like I mentioned, I need to select plane 183 element. That plane 183 element is listed under the solid type. So here you can see that 8 node 183 will be there. So I need to select this and click OK. So we will get plane 183 here. So under this plane 183, like I already mentioned, in case of two-dimensional analysis, you have three different types of element behavior. So either you can have a plane stress option, you can have a plane strain option, or you can have an axisymmetric option. So in this problem, we are discussing about plane stress, and also we are not consider the thickness as 1 unit. So we consider some thickness also here. So therefore, I need to use the option plane stress with thickness option I need to use. So that element behavior I can set here to under options. If I select these options here, see element behavior, the key point 3 option number 3 in the key point options. So you have element behavior. So obviously this is a quadrilateral. Element shape is quadrilateral only. So if you want to change it to triangle, so like in the element description I said, the element can have either 8 nodes or 4 nodes. If it is a quadrilateral element, you have 8 nodes. If you use this triangle option, you have only 6 nodes. So that means 2 nodes are degenerated or merged into some other nodes. So therefore, total you have only 6 nodes. So whatever default is there, I'll take this one as quadrilateral only. Then the element behavior, if I go to the element behavior, here I need to take plane stress with thickness option because I want to input the thickness as 10 mm. If I don't, if I take only plane stress option here, it will take the thickness is 1 unit. That means 1 mm. Whatever the dimensions I follow, it will take 1 unit in that particular dimensions. But in a per hour plate, he has given the thickness as. So therefore, to input that, I need to use this option, plane stress with thickness option. So click OK. Then once it is added, you can close that. Then I want to define the thickness. So the thickness is defined through this real constants. So I need to click on this real constants. Then I need to click on add. So now it is nothing is defined right now. So I need to define the thickness. I need to click on this add. So then I have to select the respective element. So then I need to click OK. So then it is asking for the thickness. So I'll enter the thickness as 10 mm. Click OK. Then close this. Then we need to define the material properties also. So like I already told in some of the previous problems, even though you don't require material problems in order to solve this problem analytically, but in the software, if you want to solve the problem, it is must to input the properties. Even though if I take that analytical solution, if I show it here, so in that analytical solution, you don't require any material properties here. So Only thing is what you required is load and only area. So with this you can get it. But here, even though that is not required, the software won't solve the problem if you won't give any material properties. So we need to input some material properties here. So then generally what I'll do is I'll assume the properties are the plate is made of steel. So I'll give the properties of the steel. So steel is going to be a linearly isotropic material. I'll select that one, and 2e power 5 is the Young's modulus for the steel in MPa, and 0.3 is going to be the Poisson ratio. I'll input those properties and then I'll click OK. Okay, so that means, of course, the material properties are not required for actual our problem to compute the stress concentration factor, whatever you want. But software won't solve you your problem if you don't define material properties. That's it. So I define the element types, I define the thickness in the real constants, then I define the material properties. Then I'll go for the modeling. That is, first I'll create the geometry. To create the geometry, I go for modeling, create, then I need to go for areas. In that, I have to create a rectangular area. So therefore, I'll click on rectangle. So I'll use, you have different options here. You can use any one of those three options. So I'll favor this one. By dimensions, I want to create it. So here, the length of the rectangle is 1000 mm. So what I'll do is, instead of 0 and 1000, I'll give, here it is asking for what is x1 and what is x2. So that means what I'll do is, I'll give x1 is minus 500 and x2 is 500. If you go back to that diagram what I have shown to you. Okay, here. So here I want to take the origin at this location. So that means origin, I am fixing the origin at the center of the hole. So therefore this is minus 500 and this is minus 500. Then if I take the width, this is plus 250 and this is minus 250. Like that I'll give. Why I am giving that one is because I want to create the hole at this location exactly at the origin. So in order to create this hole, it will ask for where you are, what is the center of the hole. So then if I select 0, 0 is the center of the hole, then that is going to be somewhat easier or convenient to me. That's why I'm defining the area is something like this, minus 500 to 500, and that is the rectangle, and then minus 250 to 250. This is another one. So now if I click OK, so now a rectangle will be created. See that the origin is exactly at the CG of this rectangle. Exactly at the CG of this rectangle. So now first I created the area, a rectangular area. So now to create the central hole, first I need to create some solid circular area. So I'll go for circle, then solid circular area. So then now it is asking where is the center, that is what is the center of that circle, that is what is x coordinate, what is y coordinate. So I want to create the center at 0, 0. I can pick it or else I can leave the blank. So then it will take it as zeros. Then I need to create a hole whose radius is 25. In the problem has given the diameter as 50 mm. So therefore the radius is going to be 25. So click OK. So now a circular area is created here. But so now in order to create that hole here, what I have to do is I have to subtract the circular area from this rectangular area. That I will do in the modeling through Boolean operations. So you have an option in the software which is called operate. Under operate you have that Boolean options. So in that I can subtract, I can add, I can divide, I can glue, overlap, or so many things I can do that. So but here what we want to do is we want to subtract the areas. So I'll use the subtract option. Then I have to select areas because I am subtracting the areas. So if I click on these areas, then a dialog box will come up to you. Then you need to select the two areas which you are going to subtract. First I have to select the base area. So now it is saying that, see, there are two areas at this location. The picked area is 1. So then, okay. So if I satisfy this message, then I'll click OK. Otherwise, if I want to shift the next selection, say now if I do that, now the selected area is, or picked area is 2. So now this area is selected. So then if I satisfy with the selection, then I click OK. Otherwise, I'll click on next. So now it is turned to something like this. Then first I have to select this rectangle, then click OK. Then again I need to select the circle, then I need to click apply. Okay. So then plot, you go for plot multiplots. Okay, so what we did, subtract areas. So I need to select this, pick one, okay. Then I need to select the next area. Picked area is 2. Then click OK. Why it is not showing? I don't know. Plot, multi-plots. I'll see how many areas are there. Maybe there may be some graphic problem. Still there are 2 areas. Okay, so what I'll do is, I'll try to do it again. So booleans, subtract areas, then I'll pick this area. The next area is only 2. Okay, next one only. Okay, then I select this. Okay, still it is selecting only this. So here the area number 2 is it is showing. So click OK. Plot areas. I'll go for that. So still it is showing something. What I'll do is, I'll redo this again. So maybe there may be something is wrong in this. More number of areas has created. First what I'll do is, I'll delete all the areas. Delete areas, pick all. So now nothing is there. I'll create again, once again. I'll go for rectangle, by dimensions. So obviously these are the dimensions. I'll click OK. Then I'll go for again area, solid circular area. Then the radius is 25. Click OK. So now it is created. Now I'll go for operate, subtract areas. So first I'll pick this. Okay, I'll click OK. Then here I need to apply. Then I need to pick this area, next area, next one, this one I need to select. I click OK here. Then I click apply. Okay, see now it is created. Maybe earlier there may be some issue is there. I don't know what is that. So, but now our role is created, right? So like this, what you have to do is, first you have to select this area, then apply, then you have to select this area, then you need to apply. So therefore, the hole is created now. So now for this hole, now what I need to do is, I need to convert this one into FE model. So for that, I'll go for meshing and mesh tool. So in the mesh tool, first what I do is, I'll set the edge length. So that means what is the minimum edge length I need to consider is, I'll take it as, because this dimension is 1000 and this dimension is 500, I'll take the edge length is some 20 mm. That means along this line you have 50 elements, along this length or along the height you will have 25 elements. So I'll do like that. Then I'll go for mesh, click on mesh and select this area so that meshing will be done. So this is going to be learn something like this. But if I observe the mesh around this hole closely here, you can see that if I zoom this, see your circle is now modeled as something like a octagon or some polygon. So maybe depending upon the number of sides here, 1, 2, 3, 4, maybe octagon, but it is not representing exactly the circle. So therefore what I need to do is, I need to refine the mesh at this location so that actual circular shape can be represented through your FE elements. So this is what we call it as a, in FE terminology there are different types of errors. So this is what I can call it as a discretization error. So that means I have not done the meshing properly. So to avoid this discretization error, what I need to do is, I need to refine my mesh. So for that, here you can see in the mesh tool, you have a refine option is there. If I click on this refine, then it is asking what is the, at what location you want to refine. So what I'll do is, I want to refine around the circular hole. So then I'll pick the circular option here. Then I'll draw circular something like this. So around that hole. So then I'll click OK. Then it is asking for what is the level of refinement required here. So I'll go for the maximum level of refinement. So then click OK. So now what it will do is, it will remesh the hole. Now you can see that. Now if I zoom it here now, you can see the actual circular hole now. So now your mesh is fine here, so that there won't be any discretization error now. So now I am satisfied with this mesh now. Then if I am satisfying with the meshing now, next what I'll do is, I'll go for the loads and boundary conditions. So I'll go for, first I'll define this end is fixed, apply structural, displacement on lines. I can apply to the geometry direct straight away because it is a line. So if I want to apply for the elements, I need to select these many number of elements. Instead of doing that, I'll apply for this line straight away. I'll click OK. So all degrees of freedom should be constant. I'll click OK. So now it plays the constant. Similarly, I'll apply that pressure load on this line. So for that, I'll go for pressure on lines. I'll select this line, then click OK. So then it is asking for what is the magnitude of that load. So inside it is a tensile load, I need to take it as minus 200. Minus 200 Newton per mm square. That's it. So this end is fixed and this end is done. So then once you've done this, then what you have to do is you need to go for solution and then you need to solve the current load step. Okay, so once you done properly, it will solve for you. So then close this. After solving that, only one result we need to look at it is what is the maximum stress value, maximum normal stress value in this. That you can either do it by plotting or you can do it by listing also. So first I'll go for plot, nodal solution, then degree of freedom solution. Stress, not degree of freedom solution. We are looking at the stress values. You have to select X component of stress. See, it will show you. So this entire stress is going to be only uniform, should be equal to, this is equal to your 200. If you look at the color, maybe it is close to the 200. But what I want to look at is, I want to see the maximum value. Here we have shown it as 612.486. So where it is located? See, you can see that if I zoom this area here, in the vicinity of the circle, exactly at the 90 degrees here, you are going to have maximum stress value. MX symbol is there. You can see this one and this one. That value is going to be 612.48. So then I'll capture this image and I'll put this one as a something, some image in our record. So variation of normal stress in the plate, like that I take it. So I can, so to do that, what I have to do is, I need to go for plot controls. In that you have an hard copy option. Then you need to use to file option. So then here you need to use the reverse video option. Then whatever you want, whether it is bitmap, TIFF or JPEG you want, you can select that and just click OK. Obviously in your working directory it is going to be saved. So you take that and you paste that in your okay, so it is there in the D directory for me. If I open that, okay, like this, you will get the image. You take this and straight away you can paste that image into your record. So this, if you want this white space, if you don't require, then you can crop this also using either a Paint or some other editing software. You can do that. You can paste this one into your record. But coming to the calculations here, so I got the maximum stress value. Then I use the formula to compute the nominal stress. So from this, so we got the stress value as 612.5. Then I can use this calculation, this graph, this calculation. So if I compute that, it comes out as around 2.75. From this analytical graph, what we are getting it as 2.7. So now I can compare those two values also. So like this, I can solve the problem. So if I want to list the result also, you can list the result. So that is, but if you list it, you don't know where exactly it is, the maximum stress occurs. So for that, what you have to do is, again, first you have to list the solution. Then after listing out, you need to identify where the location it is going to, where is the location also, just by identifying the element number and all these things. So that is going to be somewhat tedious. But here, instead of doing that, if you go for plot, you know everything. See here, the maximum stress values, SX value, you can see that it is at node number 310, it is maximum. So 3612.49, that means approximately 312.5. So here, if I want to know where this 310 load is located, so for that, what I need to do is, I need to go for list nodes. So in that, okay, so whatever format you want, you can select here. Either you can sort by coordinate or sort by node number, you can do that. So I'll keep default things only. So then I'll go for that node number, whatever I taken here, that is 310. So in this, if I go down, I can easily identify the location of that node number 310 also. 310, where it is, page up. Maybe it is not here. So somewhere I'll go down, go down, go down. That is somewhat because you have so many number of nodes, identifying that particular one. So it will be there in this list, but only thing is you need to check this properly. So Control F is going to work. I don't think so. It is not going to work. What I do is I'll do instead of listing by general default settings. What I'll do is I'll list by something like here. I'll take X coordinate. The first criteria for sorting as X coordinate. Then next criteria is Y coordinate. I'll select something like this. Then it is easy for me to identify that node now. So now we can see that. So exactly at that location, what is your X coordinate? X coordinate is 0. And your Y coordinate should be 50. So then I can identify that. So X coordinate 0, first I'll go to that location. Okay, here, yes. See, you can see that T310 is at a location of X coordinate is 0 and Y coordinate is -25. So in the bottom, or +25 also you have, that is the top. You can take like this. So you can identify that at node number 310, it is maximum means, see whatever is shown in that in that contour plot also, it is showing the same thing. So this is the location where your X coordinate is 0 and Y coordinate is -25. So like that also you can identify the location of the maximum stress also. Okay, so I think this is how we can solve the problem. So this is what I want to explain or I want to discuss with you. So I think yeah, I have done with this. If you have any doubts now, any doubts or any query, now you can ask. Because it is already 10:05, so I'm not going to take up the second model. What is the symmetric one? Maybe if time is there later, we can see that, we can discuss about that one. If you have any doubts, now we can ask. If you don't have any doubt now we can close it, no issue. So okay, if it is clear to you, then you can leave. So just respond to that attendance sheet and then you can leave the class. I think I already placed the attendance sheet also. Maybe there is a little bit of correction is there in that. Okay, I'll do that later. I'll update that. Maybe I already told to you what is the error in that. Okay, maybe most of you given the attendance also, no issue. Okay, so if you have any doubt, then you can ask. Otherwise, you can leave the class. If you don't have any doubt now, don't stay in the class. Just leave and attend the next class.